Okay, now a graphing calculator or computer displays a rectangular portion of the graph of a function in a display window or viewing screen, which we refer to as a viewing rectangle. So in section 1.4, we'll be discussing graphing calculators and computers. The default screen often gives an incomplete or misleading picture, so it is important to choose the viewing rectangle with care. If we choose the x values to range from a minimum value of x min equals a to a maximum value of x max, which is equal to b, and the y values to range from a minimum of y min equals c to a maximum of y max is equal to d, then the visible portion of the graph lies within the rectangle. So the interval a to b by the interval c to d is equal to the order pair xy such that x is in between a and b inclusively and y is in between c and d inclusively, which is shown in the figure. So we refer to this rectangle as the interval a b by cd, which is the viewing rectangle. So you can see here that here is the value of AD, AC, BD, and BC, and then these are y equals d, x equals a, y equals c, and x is equal to b. So that is your viewing rectangle. Okay, now let's take a look at this example. Now the graphs are already inputted there, but I'm going to show you on the graphing calculator what are you going to have to do here. So what we want to do is we want to be able to choose a good viewing rectangle. We want to draw the graph of the function, which is f of x equals x squared plus 3, in each of the following viewing rectangles. So I'm going to go ahead and pull up my graphing calculator. Okay, and so we want to go ahead and then put in the function. So we're going to go ahead and select y equals, and then put in the equation x squared. So this is our x, and then we're going to square it, and then we're going to add 3 to it. Okay, so I'm going to go ahead and select graph. So currently there is our graph. Okay, now this is what our graph is going to look like. But let's go ahead and select the range by setting the following values. So in order for us to set the range, we want to pick window. Okay, and now in window, for the -2 to 2 and by -2 to 2, so the x minimum is going to be, make sure you have the negative sign. Don't press the minus sign or it'll give you an error. So you have -2 as the x minimum, and the x max is +2. And then we're going to change the y minimum to be -2. And then we have the y max at 2. Now let's go ahead and graph that. Now when you graph that, you will notice here that the graph is not in the display. And that's why it's important to understand the viewing rectangle. So here, this graph should represent this graph. Okay, so I'm going to move this over. And now in part B, what I'm going to do is now I'm going to change my window. So I'm going to go to the window and change this to -4 for my minimum, 4 for the max, -4 for the y minimum, and 4 for the max for the y value. Now I'm going to go ahead and hit graph. Now when you hit graph, you can see how there is your graph and how that's associated there. Okay, so there's your graph here. Now again, changing the windows, the viewing rectangles by your by what's given for each particular question. All right, now let's take a look at C. So we have an x min of -10, x max at 10, y minimum -5, y max at 30. So again, I'm going to go to the window, and I have -10, and then I have +10. Then I'm going to go down further. I'm going to have -5 for the y minimum, and then 30 for the max. So now when I graph that, now you should be able to see something similar to this graph, and there is that window. So again, we're trying to figure out which one is the best one to look at. Okay, so therefore there is that one. And now let's go to D. So again, we're going to go to our window, and we're going to change this to -50, and then now 50, and then -100, and then to 100. Now we're going to go ahead and graph. And so now you're going to see this graph. Okay, so if you look here, the graphs for the viewing rectangles in part B, C, and D are also shown in this figure. So we want to observe that we get a more complete picture in C and D. But in part D, it is not necessarily clear that the y-intercept is actually 3, but you can see that in the C graph. Now we see from example 1 that the choice of a viewing rectangle can make a big difference in the appearance of a graph. Often it's necessary to change to a larger viewing rectangle to obtain a more complete picture, a more global view of the graph. Now in the next example, we're going to see that knowledge of the domain and range of a function sometimes provides us with enough information to select a good viewing rectangle. So let's go ahead and take a look at this example here. So for example number 2, we want to determine an appropriate viewing rectangle for the following function. Okay, so the expression, we need to figure out what the domain of this function is first, in order for us to be able to then decide what our best viewing rectangle is. Okay, so what we do know is that inside the radical of an even root, that we need to make sure that 8 minus, erasing here. Minus 2x squared is greater than or equal to 0. Okay, and then we're going to solve for x. So I'll solve this all the way. So you got negative 2x squared is greater than or equal to negative 8. Divide both sides by negative 2, and then we have to flip the inequality. So we get x squared is less than or equal to 4. So what does that mean? So since we have x squared which is less than or equal to 4, which then implies that if we take the square root of both sides, then taking a square root of both sides would then give us the absolute value of x, which would then be less than or equal to 2. Because of taking the square root of both sides, we also need to take into account that it now becomes the absolute value of x, which is less than or equal to 2. So what does that mean? Well, the absolute value, what that implies, and what we've done, if you remember in intermediate algebra, which means that x would have to be in between negative 2 and 2. Okay? So the domain of this function would then be negative 2 to 2. So now, because of the domain is the function, right, we also need to know what is the range of this interval. So we know that in order for 0 to be less than this function, we would know that this entire function would also be less than or equal to the square root of 8. Okay, because it would have to be less than that. This would be greater than that. And then the square root of 8 would then be 2 times the square root of 2, which would then equal approximately 2.83. So therefore, the range I'm just going to write R here. So the range of this function would then be the interval 0 to 2 times the square root of 2. So we choose the viewing rectangle so that the x interval is somewhat larger than a domain, and y interval, which also has to be larger than the range. So what we can do is, by looking at this, we're going to change and put our viewing rectangle so that we can see our graph much better. So the viewing rectangle would then be the following. So we're going to go from -3 to 3. And then we're going to go one smaller than a 0, so that's going to be -1. And 2 times the square root of 2 is 2.83. So that's close to 3, so we can go up to 4 for the y min and y max. Okay, now let's go ahead and then put this graph into our function. So I'm going to come in here, I'm going to clear my graph, and then I'm going to put in the function second square root eight minus 2x squared. Then I'm going to go ahead and change my window to be -3, and then 3, -1, and then 4. Now when I graph, now you should see what this graph looks like. So again, sometimes you might have to, find the domain in order to then be able to clearly see sort of what that graph is going to look like. All right, let's go to example 3. Okay, now here we have the graph of the function y equals x cubed minus 150x. Okay, so here the domain is going to be all real numbers. But that doesn't help us choose a viewing rectangle. So let's experiment with the viewing rectangle. So I'm going to go ahead, put this in the calculator. So we're going to put our graph in here. And we have x cubed minus 150x. Okay, now, again, you can see that the window right now we have -5 and then 5, -5 and then 5. Now, when you graph that, you basically see this vertical line. Okay, so it appears blank, but actually the graph is so nearly vertical that it blends in with the y-axis. So now let's change our window to be -20 to 20 and make this -20 to 20, and let's graph. Okay, well now we can see that there's what? We get a picture that's shown in this figure down on your bottom left here, and the graph appears to consist of vertical lines, but we know that it can't be correct. So if we look carefully while the graph is being drawn, we see that the graph leaves the screen and reappears during the graphing process. So what this does is it indicates that we need to be more in the vertical direction. So we need to change the viewing rectangle. So we're going to leave it at -20 and then 20, and then let's go to the y, and let's change this to -500 to 500. Okay, now when we graph there, it's showing a graph which is a little bit better than the first two, but it still doesn't reveal all the main features of the function. So now we need to increase that a little bit more. So now we need to go down and then increase the y to -1000 and then 1000. And now we are a little bit more confident that we have arrived at an appropriate viewing rectangle. Okay, so when we get to chapter 4, we'll be able to see that the graph shown in the figure does indeed reveal all the main features of the function. All right, let's go to example 4. Okay, now for example 4, we have a function, and this function is sine of 50x. So let's go ahead and put that in here. So we have the sine of 50x. Okay, so I'm going to go ahead and put the window in. So we're first going to then put in -12 and 12 for our x min and x max, and then 1.5, excuse me, -1.5 for the minimum, and then 1.5 for the maximum. So at first glance, the graph appears to be reasonable, but if we change the viewing rectangle to the one shown in this here, you can see what happens to the parts of each graph, and they look very different. So something is strange is happening here. Okay, so again, if you change the x minimum of it to be -10 and 10, this is what the graph is going to look like in your graph. Again, leaving the y minimum, y max at -1.5 and 1.5, if we change this to -9 and 9, then again, you're getting a different picture. And now if we go between -6 and 6, again, we're getting a different kind of picture. So the appearance of the graphs depends on the machine that you're using. So the graphs you get with your own graphing device might not look like these figures, but they will also be quite inaccurate. So in order to explain the big differences in appearance of these graphs and to find an appropriate viewing rectangle, we need to find the period of the function, which is y equals the sine of 50x. So hopefully I can get this to work here. So when we have y is equal to the sine of 50x. Okay, so we know that the function, the sine, has a period of 2. Not 2, 2 pi. Okay, and then the graph of y equals sine of 50x is shrunk horizontally by a factor of 50. So therefore, we would have 2 pi divided by 50 which if we reduce that, it's pi over 25, which gives you approximately 0.126. Okay, now what this does is this suggests that we should deal only with small values of x in order to show just a few oscillations of the graph. So we would choose the viewing rectangle of the following. So our x minimum and x max would be negative 0.25 and positive 0.25. And then we would leave our y min and y max at 1.5 and negative 1.5. And so now we can see that the oscillations are so rapid in the figure here and you can see that it misses most of the maximum and minimum points and therefore gives a very misleading impression of the graph. So we have seen that the use of an inappropriate viewing rectangle can give a misleading impression of the graph of the function. In examples 1 and 3, we solved the problem by changing a larger viewing rectangle. In example 4, we had to make the viewing rectangle smaller. Now, in this next example, we look at the function for which there is no single viewing rectangle that reveals a true shape of the graph. So the graph of the function f of x was equal to sine of x plus 1 over 100 times the cosine of 100x. So if you look at figure 8, okay, it shows the graph of f produced by a graphing calculator with a viewing rectangle of negative 6.5 by 665 by negative 1.5, 1.5. Okay, so it looks much like the graph of y equals the sine of x, but perhaps with some bumps attached. Now, if we zoom in the viewing rectangle of negative 0.1 and 0.1 by negative 0.1 and 0.1, we can see much more clearly the shape of these bumps in figure 9. So the reason for this behavior is that the second term, 1 over 100 times the cosine of 100x, is very small in comparison with the first term, meaning sine of x. So we really need two graphs to see the true nature of this function. Now, example number 6, we want to see eliminating an extraneous line. So we're drawing the graph of y equals 1 over 1 minus x. Now, in figure 10, in the first figure on the left, which is part A, the graph produced by a graphing calculator with a viewing rectangle of -9, 9 by -9, 9. So in connecting successive points on a graph, the calculator produced a steep line segment from the top to the bottom of the screen. Now, that the line segment is not truly part of the graph. Notice that the domain of the function, y is equal to 1 over 1 minus x, where x such that x cannot equal 1 because it's a restriction. So we can eliminate the extraneous near vertical line by experimenting with a change of scale. So then we change the smaller viewing rectangle to the following. We got -4.7, 4.7, and -4.7 and 4.7. So in part B, you can see that we can obtain a much better graph. Now in example 7, it says how to get a complete graph of the cube function. Graph the function y is equal to the cube root of x. Now, some graphing devices display the graph shown in the first figure, which is figure 11, whereas others produce a graph like that in figure 12. So we know from section 1.2 that the graph of figure 12 is correct. So then what happened in figure 11? Well, the explanation is that some machines compute the cube root of x using a logarithm, which is not defined if x is negative. So only the right half of the graph is then produced. So you should experiment with your own machine to see which of these graphs is produced. Now, to understand how the expression for a function relates to its graph, it's helpful to make sure that you know how to graph the family of those functions. So if you can graph those on your graph, then the collection of those functions whose equations would be related to what you can use with your calculator. Now, in the next example, we graph members of a family of cubic polynomials. So we're going to graph the function of y is equal to x cubed plus c times x for various values of the number c. And how does the graph change when c is changed? So if you take a look at the figure here, okay, the graphs of y equals x cubed plus cx for when c is equal to 2, 1, 0, -1, and -2. So we see that for positive values of c, the graph increases from left to right with no maximum or minimum points, meaning peaks or valleys. Now when c is equal to 0, the curve is flat at the origin. When c is negative, the curve has a maximum point and a minimum point. And as c decreases, the maximum point becomes higher and the minimum point lower. Okay, now solving an equation graphically. Now, this is probably one of the most important examples here because you'll be doing this at some points in time during your lessons. So we want to find the solution of the equation cosine of x is equal to x, correct to 2 decimal places. So the solutions of the equation cosine of x is equal to x are the x coordinates of the points of the intersection of the curves y equals the cosine of x and y equals x. So what you're doing is that you're graphing both of them on the graph. So let me go ahead and do that here. So if we graph both of these on the same do that. So we have the cosine of x, and then we're graphing x. Okay, so this seems pretty close to the first one, right? But we want to be able to see what is that value, meaning that where does it intersect? So here, they have to use a different viewing rectangle here. So what they're doing here, if you look at part C, okay, the x scale is then changed to 1, 0.1, and then 0.1. So let's go to the window. And so if we take a look at the first one, we have -5, and then 5, and then -1.5, and 1.5. And then if we go down, oops, I missed that there. So this should be -1.5. And then the scale for the x scale is 1. So again, that's going to give us our first picture. Okay, because again, we want to locate the roots of this function. So now if we go a little further here and go ahead and put this in, so let's change our window to 0, 1, and now our scale is now at 0.1, and then 0, and then 1. And we graph, okay, we can see something similar here. Okay. Now, if we change our window to what we see in part C, so we have 0.7, 0.8, and the scale is now at 0.01, and then again 0.7, 0.8, okay, we can see that. So by looking at all three of these graphs, let's go ahead and sum this up again. So the solutions of the equation are the x-coordinates of those points. Okay, so from the first figure, we see that there's only one solution here, okay, that lies in between the values 0 and 1. So here's the value of 0, here's 1, and there's one solution. Now, if we zoom in to the viewing rectangle here, okay, and we're looking at 0 and 1, and then 1, we've shrunk this video, and now we can see that this value is not, it can be closer. So you can find out, instead of it being in between 0 and 1, that it could lie in between something smaller. So it could be in between 0.7 and 0.8. So now if we change our x-min and our x-min here by moving the cursor to the intersection point of the two curves, or by inspection the fact that the x scale is 0.01, we see that the solution of the equation is about 0.74 here. And if you hit trace, okay, let's go ahead and trace. If you hit up arrow and hit down here, okay, right here you should see that you have 0.74 and 0.74. So therefore, that's why it's saying that the solution is about 0.74.